Hello and welcome. My name is Monisha Ghosh. I will be joining the Electrical Engineering Department at the University of Notre Dame and the Notre Dame Wireless Institute in January 2022. A little bit about my past. I worked for 24 years in industry at Philips Research, Bell Labs Research, and InterDigital before I joined academia in 2015 at the University of Chicago. I have also had 2 leaves of absence while at U Chicago, one at the National Science Foundation, or NSF, managing wireless research portfolio there, and most recently at the Federal Communications Commission, or FCC, as the Chief Technology Officer. I'm very excited to be joining Notre Dame and hope to bring my industry and government perspective into the wireless research program at Notre Dame. I'll spend the next few minutes giving a short overview over a couple of past research projects and my plans for future research. My current research is focused on 2 broad areas around the common themes of spectrum management, measurement of real-world usage of spectrum, and how these would inform the design of next-generation cellular and Wi-Fi networks, such as millimeter wave. As the discussions around 6G are already starting, it is becoming increasingly clear that the mid-band frequency range of 2 to 10 gigahertz, which provides a balance between range and available bandwidth, will be where next generation systems will want to deploy. However, as you can see from the table of US frequency allocations, there is very little clean, unallocated spectrum left in these bands. A variety of federal and communication systems, commercial systems, are already deployed, and hence new services will need to find better ways to coexist with incumbents and each other. So I will talk about 2 specific areas of research that I've been involved in over the past few years that are relevant to this research area. The first is coexistence and spectrum sharing, and the second is smartphone-based spectrum sensing. So my first area of research is spectrum coexistence. Specifically, we studied the coexistence of Wi-Fi and LTE LAA in the 5 gigahertz band using analysis, simulation, and experiments. On the analysis side, we modified Bianchi's method to theoretically analyze coexistence with different detection threshold and transmit opportunities. And we showed that symmetrical thresholds deliver the best performance for both Wi-Fi and LAA. This result, while important from an academic point of view, was also presented to the standardization bodies and was influential in ETSI brand, which is an international standardization committee, which have adopted a symmetrical threshold of minus 72 dBm for 6 gigahertz, which is the new unlicensed spectrum that is coming online, unlike what we have in 5 gigahertz. Our analysis work has always been corroborated by simulations. We've enhanced the coexistence module in NS3 to perform system level simulations, where we can have a lot more flexibility and allow different configurations for testing. We have also concurrently done experiments, starting off with lab experiments using NI, USRPs, or software-defined radios, with the Wi-Fi and LTE application frameworks. And we've also set up Wi-Fi routers and devices to perform testing in lab environments. Our very recent work, which is what I will talk about a little bit more in detail, is using field deployments of Wi-Fi and LAA to quantify coexistence in the real world and in hidden node scenarios. One of the themes of my current research approach is to always try and verify what we're seeing in analysis and simulation and small lab experiments with what we're seeing in the field. So here is the experiment setup that we had in the University of Chicago. The building you see there is the bookstore, and right opposite the bookstore there is this pole, which is actually an LAA-based station that's mounted on the top. The experiment areas are shown and the distances are shown in this diagram here. And what you will see is that this is a really nice hidden node scenario where we can test how the effect of LAA the effect of LAA on the performance of Wi-Fi client devices that are outside in front of the bookstore and associating with these access points. So we've done a number of detailed experiments, and we've got a few papers that we've written on this, but let me just put out one result that is very interesting. On the left, you will see the throughputs on the y-axis. For different kinds of devices, we used 5 different handheld devices, and for different kinds of traffic. We had data, which is D, data plus video, which is red, streaming, which is yellow, data plus streaming, which is green, and video, which is orange. The first thing we noticed was that as soon as we activated the LAA network, and that's the curve that you see on the right, the throughputs of all of the Wi-Fi devices dropped significantly. This is almost an 80% or sometimes 90% drop in throughput, except for the case when all devices were using streaming video. And the reason for that was that the networks do not allocate streaming video on the unlicensed band for quality of service. So this was something we had not really expected in all of the analysis and simulation work we did. And we had not also expected such a dramatic decrease in throughput in this interference scenario. So we are following up on this work. These are, we believe, the first detailed experiments done in academia of how Wi-Fi and LAA coexist in practice. We uncovered a number of existing problems that we were not aware of, and neither was existing literature. And we're following up on this in our future research. And we showed that even though the conventional wisdom says that if Wi-Fi is deployed indoors and LAA outdoors, in typical outdoor Wi-Fi usage, which is very prevalent on college campuses, we observe a fairly severe degradation of Wi-Fi performance. We continue to make measurements with different scenarios and combinations of Wi-Fi and LAA. Right now, we are currently replicating this experiment in simulation. This will allow us to change parameters such as sensing thresholds, transmit opportunity duration, etc., to optimize coexistence performance. And we hope that our future work in this area will influence 6 gigahertz coexistence, where we are going to be studying coexistence between 11BE and 5G NRU, just as we were able to do with our work in 5 gigahertz. I want to switch gears into the next area of research that I want to talk about today, which is smartphone-based sensing. Sensing is an integral part of spectrum management. And there are 2 ways that one can do it. One is by using dedicated sensors, very much like the Radio Hound project in Notre Dame. The other is by using sensors that all of us are carrying around, which is our smartphones. So for example, a Google Pixel 5 today, it just came out about a year ago, it supports frequency bands all the way from the low band to millimeter wave. And this list will continue to grow as new spectrum comes online. For example, the C-band spectrum or the 3.45 gigahertz spectrum. And as new spectrum gets allocated, all the smartphones will start using them. So when you look at this list, you see that just using the RF front ends that you have on your phones, it is very easy to get a very broad picture of how spectrum is being used on the ground, literally. And that is what we set up doing. Today, there are a number of apps that are available for extracting information from your phones. There's Network Signal Guru, which is a commercial app that we've used. There's Mobile Insight, which is developed by Professor Chinny Peng at Purdue, which captures higher layer information. And there are many speed tests apps, including FCC speed test app, which we use a lot because it allows the data to be exported. However, the one that we've been using the most is an app that was developed in my group. We call it SIGCAP, and there's a link. It is freely available for download. It runs only on Android. We can capture Wi-Fi and LTE information, all the information that's available via the Android APIs, the BSSID, RSSI, PCI, RSRP, RSRQ, the frequency band, the bandwidth for the primary channel, GPS information. And of late, we have added the APIs that extract skin temperature and CPU temperature from the phone. The reason we've done that is because we very recently discovered that the throughput that you get on 5G millimeter wave depends on how hot your device is getting. Now, this app does not require root access. The data export is very easy. We download all the data, we create CSV files, and then we can do our analysis on top of that. The data is passively collected every 10 seconds in the background. It does not activate your data carrier. The cons of this approach is we do not get a lot of detailed information about the 5 parameters since we do not have root access, and the aggregated channel bandwidth is not available, and we do need an active SIM card for each cellular carrier. But what does this let us do? We can map infrastructure deployments and signal strengths very easily. We can very quickly determine potential areas of LAA and Wi-Fi overlap, which is how we used this app when we started out. We determined where new technologies are being deployed. We realized that CBRS is being deployed in Hyde Park just by my student riding a bus with SIGCAP turned on his phone. We can use it to track down interference claims or identify underutilized spectrum, e.g. UNI2, where we have detected very few Wi-Fi access points. And we can crowdsource measurements, of course, with the caveat that user location will be disclosed, but we do not capture any other private information other than the RF signals that your phone is seeing anyway. We have used this to verify coverage claims by carriers. When combined with speed test apps such as the FCC speed test app, we can obtain throughput and end-to-end latency performance, and that allows us to get a very complete picture of what is actually going on with our networks. And we've also started looking at propagation modeling. Most propagation modeling that has been done in the past and even today is done by people setting up special purpose transmitters and receivers and looking at the propagation. However, as we all know, that is not how the real world works. Your transmitters are on lampposts, they're on top of buildings, they may be obstructed by trees and other objects. And your transmitters are not your professional receivers. Your receivers are your handsets. They're not professional. And so by actually capturing RSRP very, very densely, we can begin to do propagation modeling in the real world and see how it compares with our models in theory. So this is an example of a website we've created where we've put all of our data. We can do PCI mapping, which allows us to actually take all of the signal strength data we have and actually locate where the base stations are. This has been incredibly useful for us as we do our propagation modeling. And we've also found this to be much more accurate than many websites that are available like OpenCell ID, especially for small cells that are mounted on lampposts. This approach was also used in the FCC USPS broadband mapping feasibility study earlier this year. A report was created on the results. As you see on the picture on the right, there were 3 phones that were strapped into a box along with the radio hound sensor. Each phone had a SIM for a major carrier, and these boxes were mounted on the side of a postal vehicle, which then, as it went around its routes, and you see all of the routes that it went around in the Colorado area, it collected information just as it was doing its normal duties. We believe this approach is very scalable. We can use it to very quickly map large areas, and we've done that at our campus at the University of Chicago, and I look forward to doing that in Notre Dame as well. We've also branched out into looking at new applications for this data. So for example, we've started looking at indoor-outdoor classification using SIGCAP data. So once we have all of these data sets that we have, and we've made data collections in indoor and outdoor locations, we can now throw machine learning tools at it on a very large data set. And we have tested it with various different sets of features. And all of this data just comes from SIGCAP. And we've tried many classifiers, and we've shown that random forest classifiers out of the box literally can deliver classification accuracies of about 98%. This is very, very encouraging because it points to a new way that we can bring in machine learning tools to study wireless networks. So the key takeaways from this research has been that our smartphones are really like mini network analyzers with the right software on it. Easily deployed, we can do crowdsourcing to map signal strengths continually. And if we add speed tests to it, we can get better information, but it also uses up data plans fast, right? So we try to use SIGCAP only as much as possible. The cons are the current APIs are limited. We don't get all the information that we would like. So we are working on ways to improve the data collection using smartphones. We also feel that the data upload, curation, and analysis is a significant component of any spectrum sensing methodology, and it applies here as well. The significant research and development that needs to be done here as well. So by this method, though, allows spectrum sensing to be more than just sensing of the RF signal level, because now we can actually capture how many packets are being used, what percentage of the time a channel is being used. And this is very, very important as we look forward to the future of spectrum sharing. And especially now, as 5G deployments mature and discussions around 6G commence, it is very important to quantify performance of networks today to understand where future research focus should be. And as I mentioned before, the data sets we are building will be used to drive AI ML-based wireless network optimization. So the goal here is to really create the equivalent of ImageNet for wireless research. We all know how useful ImageNet was for driving AI in the image processing community. We want to do the same for wireless research. So here are my thoughts about where I think wireless research should be going as we look forward to the next G. Sharing is here to stay, unlike in the future where you had Wi-Fi devoted to unlicensed spectrum and cellular systems devoted to licensed spectrum. We are going to see more and more of sharing and coexistence, just as we are seeing in 5 gigahertz and 6 gigahertz. And we need systems to start designing to this reality. So part of my research is focused on how can we build these systems, unlike systems, to coexist better. We need better propagation assumptions because sharing is only as good as your propagation models are. The role of MAC layer in spectrum sharing, we feel, has not been adequately studied, and we've started doing that. The hidden nodes that are very common in, say, Wi-Fi will exacerbate the problem when you have unlike systems operating in the same spectrum. And this is a major focus of my research right now. Spectrum sharing would also greatly benefit from tighter coupling with RF front-end research, and better antennas and better receivers make better neighbors and co-inhabitants. And this is an area where I hope to collaborate with the other faculty at Notre Dame and the Wireless Institute, whose expertise is in RF front-ends. Because I feel that receiver standards may not be too far off. We don't have them today, but they may be coming in the near future. I want to continue developing my smartphone-based sensing tools that will allow greater understanding and control of the RF environment and enable AI ML-based approaches. And I truly feel that experimental data-centric approaches for wireless need to mature, and that is going to be a major focus of my research program at the University of Notre Dame. These are a list of references and papers that we've written over the last few years on this topic. Please feel free to reach out to me at mghosh3@nd.edu. This is a very exciting field of work, and I'm excited to continue this work at Notre Dame, and I look forward to hearing from many of you. Thank you very much.